My name is David Yedwab, and our session for the rest of the morning is, does your 4G device communicate or compute? Sort of an extension, in a sense, of the previous session. This is also a repeat of a session that we did in Miami, and it'll be interesting to see how things have changed since last winter, or this past winter. We have our format is going to be we've got two presenters on our panel that will both take about 15 minutes to tell you their stories. They both play in the, for lack of a better term, the infrastructure of stuff that goes into the devices. Radios, antennas, software, all of that sort of stuff. And what we're going to be talking about those kinds of topics. After that, we'll open the floor for questions, and I've got a series of questions that I'd like to ask also, and we'll move on. But I'd like to start with a question that's for you, the audience, which is, how many of you travel with more than 3 devices? Okay, you all have to leave the room. You're not enabled enough. Bye. Okay. Our first presenter is Babak Beheshti, who is Director of Technical Marketing at Sandbridge Technologies. And Babak has been with Sandbridge since 2001, probably amongst the longest tenured positions of folks here at the session. He's been in the R&D space for a long time in wireless technology, and he's going to tell us about a lot of those things. Babak, besides his positioning, is a distinguished member of the IEEE. So he brings lots of credibility to our panel. Babak?
Let me move up to the podium. Easy to flip the slides.
While you're doing that, I'm going to see.
Good morning, everyone. Thank you, David, for that introduction. If you look at the program, I believe it says that Paul Ruman, CEO of Sandbridge, is supposed to be standing on this spot. So I'm not Paul normally, but today I am. I'm more of a technical side, so hopefully I'll be able to withstand your questions in the Q&A session. But with that, let's move on. As vision statements and mission statements are supposed to be, Sandbridge's vision statement is fairly vague. Leverages programmability to build market share leadership in smartphone silicon. Essentially, as you will be, programmability is the key word in terms of our technology. And what I would like to do in the next 15 minutes or so, impart upon you a little bit more of detail in terms of what that means in our sense. Very quickly, Sandbridge is a fabless semiconductor company based in Tarrytown, New York. It's about half an hour northwest of New York City. We also have a presence in Lowell, Massachusetts. What you see on the, I'm sorry, I got to somehow get rid of my Wi-Fi in here, and otherwise it's going to be popping up constantly.
Power stream. Okay.
We are a venture capital funded company, and you see the logos of the VCs on the right-hand side. Our mission is to deliver the, in all caps, next generation wireless baseband engine focused on multi-mode 4G, in particular LTE and WiMAX, which are the focus of attention in this conference. And as you could imagine, as it was with the 3G in its initial deployment, even today, these are islands of service, which means that you really, to be viable, you need to support the legacy technologies that transcend beyond the geographic areas that are covered by the newer standards. And as you will see, the value proposition is integration of multiple wireless standards as well as other technologies within one package, again, to reduce the chip count, reduce the time to market, et cetera, et cetera. All right, I'll skip through a couple of the slides fairly quickly. I'm sure you've seen some of these in various forms in presentations here and there. But again, the key point here that I want to take away from this graph is that, as you see, the yellow is basically the annual growth of mobile devices. The basic phones, even though, at a 500,000 million units, 500 level, they pretty much are flattening out. In fact, enhanced phones are pretty much flattening out also. Majority of the growth comes from the smartphones and smartphone features, and that's basically what's giving the the 31% annual growth. And that's basically where the value comes in terms of the context of my presentation here. Another graph that quickly I want to take a couple of points away from it is that you notice that this is the attach rates in millions of units per year going from 2005 to 2010. You notice that the Wi-Fi attach rates are pretty much reaching 100%, and you saw that in the session prior to this one as well, if you sat through that. The point being that we do have significant potential for various broadcast and cellular technologies being used by the mobile users, therefore requiring more and more functionality within what we call the smartphone, even though we will talk about even that definition is expanding as we speak. So what is it that we carry? So if you take a look at, other than the grandma's phone that would be perfectly happy with her voice connection, we do have a color screen, mostly touchscreen nowadays, a camera, which is an interesting thing that I will get into later. It's sort of given to us for free. Otherwise, I don't know if there's a compelling argument for it to be in there. Audio, obviously, if you want to have voice capability, multiple antennas, in fact, and all features require high computing performance, as you will see. Whether it is your productivity applications, whether it is your cellular, whether it is your video decoding, encoding, those require high performance. But we are all tied to the battery life. Okay, the first question that any OEM will ask any provider, any vendor, is what is your power consumption? So ultra low power consumption is a prerequisite for a handheld device that supports these features. You may have heard of the Samsung's announcement that they are marketing a low-end cellular powered phone, mainly to the India market. Again, it's simply a voice-only phone. Okay, if it had any of the features that we're listing in here, it would not be technologically viable at this point. So, what are the wireless communication technologies we're looking at? And you'll see this alphabet soup coming up a few times during my presentation. So you're looking at, for your solid voice applications, 2G, GSM. Again, in the areas that there are no deployments of advanced cellular technologies, you're looking at 2.5G, GPRS or Edge. And of course, 3G, HSBA in most of metropolitan areas, and of course the enigmatic 4G, when it's going to come and to what extent it's going to be deployed. Other than that, you just saw the 100% attach rates with the wireless LAN, Bluetooth pretty much for immediate connectivity to your headset or any storage device. It is it is ubiquitous. And then these umbrella terms, 2.5G and 3G, of course, they have their own local flavors. So in various countries, you may still have non-universal standards, as well as having flavors of the universal standards, FDD versus TDD, and so forth. So, you're looking at really 3 lines of various flavors, and this is by no means even a comprehensive list. Again, studies are showing that consumers are very much interested in broadcast technologies. 300 million TV viewers on mobile devices, latest statistics I read. So broadcast radio, broadcast TV, again associated either the existing legacy technologies or associated technologies designed for wireless devices, DVB-H, etc., as well as GPS. Okay, encryption, decryption, right? So anytime that you're using any privacy mode, your smartphone requires to run those functions. Multimedia encode and decode when you're taking videos, you're encoding. Whenever you're playing back a video, you're decoding. And games, text-to-speech, and I would put that in a very, very large category of other. There are many, many applications that fit into that other category. So essentially, you're looking at requirements of almost a general purpose computer, because you're looking at many, many different applications that are to be running on it. So, and that's where we use the term convergence platform. Essentially, it's a platform that converges those many, many technologies that are listed in there. So, what is the idea in here? You would need ideally a single platform, a single device that has the processing capability, the flexibility to run a combination of, not all of them at the same time, obviously, a combination of these technologies based on the use cases that the consumers have demonstrated, plus your memory and SIM and whatever storage capabilities that are required. And what I will not touch upon in this presentation here is one or several, which today is more practical to talk about several, RF front ends. You need radios for various bands and various technologies that you want to connect to. All right, so what does that mean? That means that you're looking at a system with an overwhelming complexity, which in fact is the case in today's platforms. So think of it this way. In case of an audio-video, you would need an audio-video decoder, encoder, which is typically a hardware block, managed by some functionality in a digital signal processor, and then managed by an overall API management software, if you will, that is running also your operating system. For your baseband processing, whatever it is, a good portion of it will be running in hardware, and then you will have it interfaced with the DSP to run some of the lower computational complexity blocks, and then your protocol stack most likely will be running in an ARM processor. If you have a DSP that is powerful enough to have the additional bandwidth required to run the protocol stack, perhaps you could eliminate the ARM and have the DSP running both your physical layer management as well as your protocol stack. And again, other cellular technologies, perhaps again with the same scenario of eliminating the ARM processor. Your GPS assisted or not assisted, again, you would need some ARM management by that. Your Bluetooth hardware, and your various flavors of 802.11, again with some IP stack running on the ARM. And of course your broadcast audio and video. So you could imagine that if you put all of these devices, if everything went absolutely flawlessly, it is a very, very complicated system. So The idea here is that ideally, if one could replace all of those individual hardware and DSP components with a singular technology under a unified API system, obviously not only it reduces the part count, the form factor, it also will significantly reduce the complexity and cost of the device. Time to market, not evident right now, but hopefully in a couple of slides I will demonstrate that to you. How are we doing time-wise?
Just speed up a little bit.
Speed it up. All right. So this slide is actually easy enough to really skip through very quickly. The definitions of various levels of SDR. SDR Forum has, basically changed their definitions a couple of times on it. Basic idea is completely non-flexible hardware radio as opposed to a cognitive radio, which is fully programmable, in fact, to the point of dynamically adapting its modulation scheme and so forth based on the channel conditions. Where are we at right now? Technology allows us to go with the tier 2, your physical layer implemented in software. The flexibility of the RF front end. There are a number of companies that are presenting this. There's a couple of forerunners available, but it is not a mature technology yet. So I would just basically say that we are around tier 2 at this point. Very quickly, again, all this is talking about is the slide, 2 slides ago that I had. The classic structure of a system would be number of fixed functionality hardware blocks, a DSP just sort of to manage and coordinate them, and an ARM processor similar to do your protocol stack and any other application that's running in there. With near SDR designs, you do boost up your DSP capability, and therefore you would remove some of the hardware blocks, but still some hardware blocks will be there. In a full SDR approach, you will have your ARM that would run your protocol stack, your OS, and so forth, and essentially, as you see, all of the fixed functionality blocks are replaced by one or multiple high-performance, low-power DSPs. All right, so I claim that the time to market reduces with using a SDR solution. Very quickly, for those of you who have been peripherally even involved in development of ASICs, you know that it is a time-consuming effort. You do your baseband algorithms, typically floating point. You do derive your fixed point algorithms out of those. You write the VHDL code for essentially to be synthesized into the hardware. You simulate the blocks, you do unit level testing and so forth. You put all of those blocks together. You do your chip simulation based on your VHDL blocks. You go through the time-consuming, expensive process of fabricating your chip, synthesizing, perhaps doing some custom blocks, doing your layout, etc. Tape out, bring the chip back. Verify it, maybe go through 1 or 2 spins. I'll even skip that. Let's just assume first spin everything was perfect out of the box. Integrate your firmware.
Has that ever happened?
Let's assume even with that, you're looking at 9 to 12 months just from your simulation phase to when you get your hands on the silicon. And altogether, you're looking at a typical 18-month time frame. Now, if magically one could completely eliminate the need for fabrication of silicon for a new system that you are developing, notice that all of that goes away. Okay, granted, nothing is perfect in the engineering world, but even cutting your design cycle into half is a very attractive proposition. And what would the design flow then look like at that point? Do your floating point algorithms, map them to fixed point, fix all of the problems that occur with the fixed word implementation, write your DSP-specific code, do any hand optimizations that are needed, either manually or automatically schedule them in your operating system and just run them on the platform. And that's it. So you don't have to manufacture a new piece of silicon, and that basically cuts down your design cycle. Again, what it would mean in the long run is that your bugs don't necessarily, they don't end up with a respin of their silicon. Simply means a software reload, either over the air or from connecting to the internet. It would mean that you can adapt to the newer versions of the standards very quickly. As we know, newer standards are always in the flux for the first few years, and it just basically makes that the flexibility a little bit more tangible in the context of your design flow. All right, so pluses and minuses. Okay, so one of the things that you always hear is the cost. For a single mode, a optimized hardware solution always beats the cost parameter, always. And that's a plus. Okay. However, for a multi-mode, the advantage goes to a flexible platform solution. If you ask me today, would I use a Sandbridge chip for a GSM-only solution? I would say only if you're out of your mind. Again, especially since I use the commodity standard as an example, but it's the multi-mode that gives you your value add. No configurability, 2 minuses. Long design cycles, we looked at it, 2 minuses. These are all relative. And power efficiency. Okay, again, one cannot beat the power efficiency of a almost at gate level optimized hardware solution. But then you look at the advantages that the SDR gives you: flexibility, ease of development. We looked at that, and something that I have only a couple of slides at the end of this slide set, which I very much doubt I would be able to get to, but I would be happy to discuss with you offline, is that now in an SDR platform you have the capability to dynamically manage your power at various levels. You could turn off individual processors within your chip. You can do frequency and voltage scaling. You could go into deep sleep. You could gate the clocking and essentially maintain the register contents, but reduce the dynamic power consumption. And you could do a lot of automatic power management by your processor being smart enough to know that if a particular unit is not being used in a particular instruction, it will gate the clock to that subunit. So a lot that can be done here at the macro level for your overall standard, as well as at micro level at the instruction set standard. All right, very quickly, this is sort of motherhood and apple pie. Your development environment should be self-contained, an integrated development environment within which one can start writing their C code from scratch, compile it, simulate it, debug it, do the performance analysis, get the cycle counts, be able to get cycle counts that are, I would say, within 10 to 15% accurate to what actually the cycle counts you get on the hardware. And once you're ready, be able to download your executable into the hardware. Okay? Wrap it up. All right. So what is the platform that I've been alluding to so far? So the SP3500 is our current production chip, which I will show one slide in terms of what goes in there. But this is only part of the solution. The chip is shipped with the standardized set of tools, which incorporate all of the compilation tools, the simulator, etc., that I mentioned to you. Standard C library. You write all of your code in standard C. No particular dialect is required in here. Best-in-class simulator and compiler, again, out-of-the-box code. A real-time operating system that manages multiple cores, multiple threads within cores, but it does have a POSIX-based API, so it's a standard-based open API. And, of course, a development board that could be at least the starting point for the developers until the custom hardware is developed. Let's skip through these. We sort of have covered these. I want to focus for a minute on the 3500 itself. Again, looks like an eye chart. I apologize for that. But very quickly, what is inside the 3500? 3 DSP cores, each running at 600 megahertz, affording a total of 30 gigamax per second processing power, essentially being able to run the entire physical layer of most of the current wireless standards, including LTE up to about 20 megabits per second data rate. An ARM processor to run your whatever applications as well as your protocol stack, and pretty much all the peripherals that one needs to use this in a smartphone platform. An audio codec interface, a color LCD interface, a USB 2.0 interface, etc., etc. We have some independent software vendors that have worked with us: Archimine in China, Mimoan in Germany, and CSolve in India. And in terms of the system designs that we've done over the past few years, runs the gamut from WCDMA back in 2001-2 time frame up to our PDA smartphone form factor that we did a couple of years ago. And these include, again, baseband and RF front-end capabilities. As I said, I will not get into this, these two slides, but there is this beast within the device called the Device Power Management Unit that does all the magic, and I'd be happy to discuss it with you offline. And one last slide, if I have time for that, David. Essentially, what I'd like to emphasize in this slide is that DSP vendors particularly pick a particular aspect that the DSP excels in, and draw a chart out of it. Okay, we're number one. We figured that really the best way to really level the playing ground is to chart numerical performance versus power consumption, milliwatts, megamax per milliwatts, if you will. And here you see the dots are various DSP processors that are around. If you see two instances of the same one, simply because there are two different frequency versions of them available. Bottom line, the higher up you are, the more performance you have, and the more to the right you are, the more power hungry you are. Ideally, one would like to be somewhere down here, obviously. So take a look at it here. Basically, what it means, if you draw a horizontal line anywhere arbitrarily, you're looking at 2 or 3 processors that have the same numerical capability, but consume power at different levels. So if you look at our old core, let's say actually the old device, SP3011, that has actually 4 of the DSP cores, one of our devices, well, actually, if you look at the one core, essentially has the same numerical capability as the C64 TI processor, but obviously at a fraction of power consumption. If you look at the 3500 right now, you're looking at essentially, in terms of its numerical capability, it's above the pack at this point, at, again, power consumptions that make it a viable candidate for a SDR solution. We're looking at for the typical wireless algorithms, about 150 milliwatts per core, and there are 3 cores, as you noticed, on that device. So with that, I apologize if I ran over a little bit, and I'll end here. I guess the question and answer will be afterwards.
Yeah,
so
right.
Let me bring up Al's.
Okay. Our next speaker is Al Petrick, who's segment manager at Skycross. Al has a long history in wireless communications and semiconductor technology. Amongst other things, he was the vice chairman of the IEEE 802.11 working group, and while Babek was talking, Al and I were teasing a bit about alphabet soup. He said is the 802.11 working group the first and only one that ever ran out of letters?
Yeah, that's true.
So we in the wireless world have certainly pushed things beyond the alphabet. Besides that, Al is also an author of the IEEE 802.11 handbook. Without further ado, Al.
Thank you, David. So my presentation today, what I'm going to talk about is something that touches the signal first and the last time out of a radio, and that's an antenna. Having been a semiconductor guy for a number of years, I always thought of an antenna as just a piece of wire. You hook it up, let somebody else worry about it, bend the metal, connect it up to it. It's changed now, right? Because a lot of the semiconductor chipsets that are out there are almost at par with each other in terms of performance. What becomes important now is the antenna, because as things get smaller, there's more antennas in there. You saw that probably in the earlier presentations, the earlier session. A little bit about Skycross. The company was founded in 2000, headquartered in Vera, Florida. It's about 10 miles south of Kennedy Space Center. About 400 employees today. Most of the designers are in Korea, Shenzhen, Shanghai, and in Taipei. We're in just about every different platform. One of the flagship cornerstone platforms was the smartphone, the Blackjack 1. We're in all the Blackjack series of Samsung, so Samsung's an important partner to us. But we're in various access points, dongles, and WiMAX applications, etc. And now we're making inroads into netbooks, notebooks, and MIDs, which I'll talk a little bit more about that. So it's clear from this that there's a lot of mobile computing and communicating devices, and there's a need for this technology. Actually, not just the technology, but some disruptive technology in these areas to make all these feature-rich opportunities become alive. So some of the wireless challenges on the demand side, we as consumers have become spoiled, right? We always want. And as technologists, we've been able to deliver and deliver and deliver. What's getting scarier is that now it's coming down to, well, I want streaming HD, very good quality, is best of wire in the home. I want to have that everywhere, anywhere. Also want full home coverage for voice over IP home handsets. So when you roam from your WAN outside and you come in the home, you want to be able to have that connectivity anywhere in a house without dropping that call. So reliable wireless connectivity is really the thing that consumers want their trust in. And lastly, they want one device that does all. So that's our challenge here for everyone in the room. How do we get there in the coming years? On the industry side, things are getting smaller. So a lot of the small form factors you see here, from PCMCI cards down to USB dongles, is really attributed to the semiconductor technology. 3-4 years ago, we were at 130 nanometers. Now we're down to 65 nanometers and approaching 45. Everything's getting integrated into radios. On the notebook side, similar form factors. Notebooks, netbooks, MIDs. The hot topic today is netbooks. They're nice and small and lightweight, and they're good to carry on the road. And they're at the right price points that are there for the consumer demand as well. So if you take a look at a netbook and a notebook, and for those of you who are not familiar with what goes inside of these things, a lot of the technology today, you'll see two sets of chipsets. You'll see all the cellular WAN in one chipset, and you're going to see all the connectivity in another set of chipsets, namely Wi-Fi, Bluetooth, 802.11, and WiMAX, GPS, FM, and other things. The antennas, you'll see, they're sprinkled across the bezel. So the bezel becomes a parking lot for antennas, or it becomes an antenna nightmare for a lot of the manufacturers that develop these products. So you'll see a camera, 2 or 3 antennas, and the challenge there is how do I get the reduced number of antennas such that I can still support all the features that the consumer wants. So traditional technologies that are used today for antenna just don't solve that problem. This technology here is called IMAT. It's our technology at Skycross. It's not a process technology. It's not component or whatever it may be. It's a design technique. It allows us to use one antenna element to support multi-bands and support multiple feeds. And through the design, electromagnetics design techniques there, we're allowed to, it just allows us to get isolations on the order of almost up to 30 dB. And that's something that we'll be making some announcements here very shortly on. Various bands, either 2.4 to 5.9 in the Wi-Fi, WiMAX 2.3 to 2.7. And now we're also taking a look at not only WiMAX, we're also in as well in the 2.5 and 3.5, but also looking at LTE as the next generation of antenna technology. If you take a look at a smartphone, if anybody's seen a teardown of a smartphone, there's a lot of stuff in there. All right, and my hat tips off to the cell phone manufacturers for making a smartphone, because it looks like building a car, right? A little miniature thing that puts a lot of stuff in there to make it happen for the consumer. But from the antenna side, it becomes a big nightmare, because isolation becomes a huge, huge issue. And depending on what frequency you're at, if you don't have enough separation between the antennas, you can't guarantee that isolation to allow those chipsets to work the way they're supposed to. So you see a little bit of an antenna nightmare to the left. A lot of the antennas are all paired, so they have a main antenna and a diversity antenna. And you'll see there in that particular diagram, we have Wi-Fi, Bluetooth. We also have a voice data and mobile video and location, which would be GPS. And to the right, it shows how do we pair and make multi-band solutions while still preserving the isolation for diversity necessary for those technologies to work. So this is an example of how disruptive technology like IMAT will be necessary going further in the future as things get smaller. So this shows an example of how we're able to reduce those antennas from 7 to 3 and actually reduce the cost from a 3 to 1 reduction. Another example here is on the WAN side. On a traditional full duplex handset, we have a switch plexer with conventional antenna technology and RF components. With this technology, and we have a few partners in this area, we're able to reduce that switch plexer as well as the RF components necessary for that bill of materials. What that does for the handset manufacturers allows them now to put other feature-rich technologies in there and actually reduce the cost of the bill of materials by shrinking the size of the PCB or adding other features that you so wish to desire in that design. Okay. Which the net result is almost a 20% savings in the RF components. Here's a snapshot of a mid. Again, the bezel itself. The mid becomes a very big challenge for everyone. And the reason for that is that you'll see the antennas that are wrapped around the bezel. There are some types, in some configurations, they're flex circuits. But as you start bringing those technologies and those features around the mid, you grab the mid with your hand. And your hand is, as you know, is water. And it's just nothing but a good absorber. In some cases, it will connect. Others, it won't. You have that kind of problem. Now you've got a return product. With the ability to take multiple bands and reduce those antennas from 6 to, let's say, 2 or 3, now it takes away that problem of the human absorption for connectivity, for not only for WAN but also for data, Wi-Fi, WiMAX, etc. So mids are coming. They're coming, but right now the hot thing is netbooks. But there's a huge challenge of how much features you want to put in and how much chipset technology you can put in there. The technology from a semiconductor is not an issue. It's the antennas. So I'll leave you with this, is that clearly we become spoiled as consumers. Consumers want everything. And we believe that at Skycross, we have the IMET technology.